Welcome everyone to this penultimate Digital Classicist seminar. Before I introduce today's speaker, always the same housekeeping announcements. There is an attendance list going around. Please make sure that you sign it. You will find it at the drinks table at the end anyway, so you have another chance to sign if you forget now. About the structure of the seminar, it will be a presentation followed by a first formal discussion, not formal because the way it's done, but formal because it's being video recorded. And after that, we will switch off the camera and move to a more informal discussion with wine and refreshments, and we'll keep going our conversation. I forgot to say, if you leave your mailing list in the attendance list, you will be subscribed to the Digital Classicist mailing list, where you get all the announcements for activities that are relevant for the Digital Classics topic. So today's speaker is Professor Harry Mendell, coming from the California State University in Los Angeles, where he teaches ancient philosophy, history of science, and a few more things. And today...
Yeah, you have to do that in America.
But yeah, I wasn't even trying to learn all of them. Yeah. And today he's going to present about visualization of ancient cosmological models. Yeah. So I leave it to you.
Thank you. And I want to thank you for having me in Berlin. I love coming here, and indeed a lot of the work I'm presenting was done here. So basically what I want to do is talk about a project of trying to make comprehensible things that are hard to comprehend. So there are basically two non-discursive modes of presenting ancient astronomy, and there are ancient modes. One, of course, is physical models, and these can come as two-dimensional diagrams or three-dimensional models. Three-dimensional models are already mentioned by Plato and presumably Epicurus, or at least that's a reasonable inference from his criticisms of the school of Cyzicus, a school of astronomers. The Antikythera device, which is getting a lot of fame lately, is really a two-dimensional, but its output is more like a digital display, although it comes in on a circular surface. All its workings are hidden to the user, so we don't see the model at all. The other sort of presentation are tables. Babylonian astronomy, of course, is mostly tables. And Hipparchus, an astronomer of the second century BCE, began presumably the Greek practice of writing astronomical tables. In a crude sense, there were tables earlier, that is to say, ways of marking the seasons of the year and the weather associated with the seasons in what are called parapegmata. In this, of course, not much has changed, except that we also use today algebraic representations of modern astronomy and also of ancient astronomy, if you look at standard historical texts. So what I'd like to do is start with Eudoxus, because Eudoxus was how I became interested in visualizations, and with a difficulty. Now, Eudoxus, I don't know if what people's backgrounds are, but Eudoxus was an astronomer of the 4th century BCE. He's the first person to attempt a geometrical representation of planetary motion. In this representation, he uses two spheres to construct a figure. So here is a diagram of that figure from Neugebauer's History of Ancient Mathematical Astronomy. It's a typical sort of diagram of the Eudoxian figure. There are some idiosyncrasies in Neugebauer's diagram which I don't need to be concerned with. But let's suppose I tried to explain it. Well, the basic idea is that you have a sphere over here with the axis there, and that sphere is rotating around. You can see the direction it's rotating, and it's carrying an axis which is here, which is rotating in the opposite direction, and the resulting figure is this figure 8 here. Did everyone understand what I said? Probably not. My guess is almost no one understood what I said, and the reason I got interested in this was because I didn't understand what I was just saying. It's extremely opaque, even with a diagram like this. It's extremely opaque. You can see the figure that results. It's a figure that goes something like that. But how that figure is constructed takes a lot of thought. Let's try something else. This is taken from my website. Can people see that? Is that a clear picture? You might want to darken it a little if you can. Can you? Yeah, now I think you can see a little bit better what's going on. Let's start with the circumference, okay? So you have a green circumference, okay? And think of that as rotating around. It's getting darker as it rotates around. I wish I had a pointer. I didn't bring a pointer. Oh, wait a minute. I do have a... Huh? Where? Is this thing? Is this a pointer?
Yes.
How do I use it?
The side is on and off.
You're dealing with someone who can't see, let alone figure things out. Well, I can do it from here.
It's the middle button.
It's the middle button,
Here.
the small button.
Yeah.
Oh, excellent. So you can see that green thing is rotating around, and it's carrying that red point, right? And that thing is rotating, as you can see, in the opposite direction, carrying the white point. And lo and behold, the white point, as you can see, is following the figure. So as this thing rotates, as the green thing rotates around, the red thing is pulling the white point back to the center, to this line here, so that it oscillates off of that line. And I think now most of you can see pretty much what's going on. All we need to add is that the rotation of the equator here and the rotation of the equator there are determined by the rotation of that pole there, the green pole, going around, and the rotation of the red pole, which is going to be connecting to that point, rotating in that direction. And so you can see pretty clearly what's going on. The visualization makes it clear. And I'm going to emphasize some of the ways in which it makes it clear, but all of a sudden something that is in 2 dimensions and static becomes something that is comprehensible. Now, did Eudoxus have such a model? I have no idea. Did he do it? But then again, Eudoxus was a very smart guy. He's smarter than I am. So I don't think you have to argue for the pedagogical value of clear representations. But when one speaks of pedagogic value, I suspect that one is misspeaking. Namely, one is thinking of teaching undergraduates or other students how to understand these things. On the other hand, I suspect that scholars working on Aristotle's cosmology are more likely to want to use the site where this is presented to understand how the models work. And similar claims can be made about all the other aspects of the representations that I have on that website. So, for example, there's a book by a guy named Koureimenos called Celestial Spheres, and in the Bryn Mawr Review, I don't know, do people know Bryn Mawr Reviews? Yeah, okay, I don't know what people know and don't know. Anyway, in the Bryn Mawr Review of Koureimenos' book, the author refers the readers to my website to understand how the models work, because Koureimenos' book is rather light on clarity there. He tries to explain how the models work without even a diagram. So I take it that that is a good way to start. So there is my website where I present lots of things with diagrams. So here is one way in which I present diagrams. But here, the diagrams aren't historical diagrams, they're just heuristic diagrams which will walk you, the reader, for example, through the proof. This is a proof of a theorem in Ptolemy with the translation here, and you can see how even in the case of a static geometrical diagram, it can help you understand the relations between things, and I think that that is a valuable feature. Let me go back to there, and this is where, well, I have presentations of the models. Oops. That's the one we just looked at, and further stuff. But I'm going to show you fancier stuff today, so there's no point dwelling on this. On the other side, tables are, and as I said, the other way of representing ancient astronomy in the ancient world. And that's fine. This is just a table of what are called chords, which are the ancient trigonomic functions. It's similar to the sine function. But it's very static. And so you can't really play with it. You're just presented with the table, and you can use the table, but you can't manipulate the table. And I think that, too, inhibits both pedagogy and understanding. So basically, starting in 1995, I started with my interest in Eudoxus and computer visualizations. In 96 to 8, there were 3 people working on Eudoxus, something that, and I think the reason all 3 of us were working on Eudoxus was all of a sudden we had access to computers, and we could construct the sorts of visualizations that I just showed you. So there are 2 basic issues with Eudoxus. We don't know very much about his models in the details. But the first question is, what's the mathematics of the models? And one can really discover things here or at least all three of us discovered things, or think we discovered things, about the models that hadn't been understood before by people who were quite brilliant mathematicians. Hagelmeyer discovered that the angle between the poles can be more than 90 degrees. If I can go back a second, let me just go back to here. The amplitude of the curve, this length, as well as the width of the curve, is determined by the angle between the poles. Oops. So this is something that you discovered, that Hagelmeyer discovered through his visualizations. Hagelmeyer and I discovered that the model does show retrograde for Mars, which was something that every writer on it had denied. And the reason we discovered it was because we could look at it visually, because mathematically it's kind of weird what happens. Javits then showed that you could modify the models to get much greater accuracy, but then you get some things that are possibly suspicious and anachronistic. I think that the lunar model of Eudoxus is also something that I got from looking at these models. I thought of the modifications of Eudoxus's lunar model primarily through thinking about how rotations work and through looking at a lot of examples. And I think I came up with the first accurate version of Eudoxus's lunar models. Now so these are questions about just the mathematics. Now the other question is fit with reality. And here understanding the models better can help us understand the empirical issues underlying the models better. Keeping in mind that there's no trigonometry in the 4th century, how much would the inventor of the models expected them to explain? And so you can look at these models and you can say, okay, what sorts of things can these models explain empirically? With Javits' models, you can do quite a lot. With the models that I work with and Hagelmeyer worked with, which are the traditional models or standard versions, they were discovered in the 19th century as reconstructions of Eudoxus, you can't do very much. But one can look at possibilities that suggest themselves and which can be combined with other evidence. For example, the loops are meant to model something, that is, a start. So one can be skeptical or dogmatic whether one is going to be a complete nihilist about observation in the astronomical observation in the 4th century, as one local Topoi member is, or as holding a very rich account of observations, such as most historians before the 1980s held, or something in between. You can look at these models, the visualization of the models, and help you understand at least what the possibilities are. And I think that is itself a useful advantage. And that is something that I think you get from looking at the models in this sort of kinematic, in a motion way, in motion and in this ability to vary the models quite easily. So in 2008 to 12, there was a virtual cosmology project at Topoi. It was basically run by Gabor Betek and István Bodnar, Tim Wagner, me, and Sebastian Szczepanski, who was the programmer, put this together. So let's turn to those visualizations. So here's, for example, we can just play this. That doesn't help you see what's going on very clearly, but we can tilt it. And now you can see that the same model we had before is even more dramatic and visible what's going on, how this point is being pulled back to its the middle here, and how the by the inner sphere, while the green sphere rotates it around, rotates the red sphere around. And then we can, of course, put it in motion. Oops, no, that's the wrong one, sorry. And we can see how, oh, wait a minute, I wanted to show you something else earlier. We can modify the angle here. You can see that as I make it more and more elongated, there it's 90 degrees. You can see that you get an enormous amplitude, which fits exactly. There's something wrong here with the electricity, because this is not generating any electricity. 1 second, let me, before the computer crashes. Oops. Now it's happy. Okay, so you can see how when you can, by changing the amplitude, and this fits in fact with an ancient criticism that you find in Simplicius of the Eudoxian models, that the latitudes were kind of funky. Going back to putting it in motion. With these models, you can then see exactly what sorts of paths you create, and you can vary the, again, vary it and see how the models work. We also did several other versions of things. We basically have a Ptolemy, Aristotle, models by Eudoxus and Calippus. Eudoxus is just as I said, his version of Eudoxus, which is very different. But I'd like to look quickly at the Almagest models, just so you can see again how this sort of visualization helps you understand how these things work. This is something that's more pedagogical than in terms of research. But one thing that we did do was, if I can go in, there's lots of different gewgaws here that you can do. Let's see. And, oops, too much. If you look over here, one of the things that we show very clearly is something that most, even people who work in the area, don't understand very well how it works, is this circle here, which is for showing the latitudes. That's too far in. I need to pull it out a bit. There we go. Oh. We need to have it move a little quicker. Oops. I'm not going to get it that way. There. 20. Is that going to do it? Oh, let's just reset it. Are you freezing on me? Let's just reset Mars. Let's look at Venus. And, oh, I know what's going on. Let's just reset it. There we go. And there we go. And look at Mars. You can't see up. Oops. I'm trying to get rid of the thing on the right, and I can't see over here. So I need to move it over here so I can see it. 1 second. Full screen, there we go. Okay. So, In all of these things, one of the things that we have in here is that you can hide, there we go. You can hide aspects of the model. So we showed the mean sun there, the average position of the sun. You can hide it or show it. You can hide the path if you want to hide the path or show the path that the planet is taking. And of course, you can do this. And we also allow you to vary all the parameters. So basically, you can see how, if you adjust it one way or another, how would that affect the motion? Let me go on. If people want to see more of that later, we can look at it. So basically, that's our visualizations, and there's lots of bells and whistles in this, but it's also important to know what's lacking in them. So most trivial thing is we didn't put in fixed star charts in it. This is difficult to do for early Greek astronomy. We didn't do it for anywhere. We weren't funded for that. We didn't put in many of the imprecise models. On my website, I have an Anaximander, but Parmenides, Empedocles, Philolaus, and Plato are absent. We would like to do that. We don't have other full models, such as Ptolemy's planetary hypotheses, the medieval Arabic models that you find in Moraga and Andalusia. The Andalusian ones are kind of flaky. Most important, we don't have any way of exporting this to a spreadsheet. And you would want to be able to take these models and find out how does it work as a spreadsheet, in order especially to compare different versions of the models, but most importantly, to compare them with real paths, which we also didn't incorporate. So there's a lot more work to do. So that's the sorts of things we'd like to do. The other aspect of it, though, is about spreadsheets. And here, unfortunately, there's a big mess, and we can thank Microsoft for that. So here's something that I did about 15 years ago, if it works. Oops. Now it's not working. Oh, there it is. I wrote, basically, if you think about what a Babylonian table is, it's basically a spreadsheet. And so I wrote a sexagesimal program in C that would enable you to do sexagesimal calculations in Microsoft Excel. So, for example, oops, why is that representing? Oh, because it's representing that. Oops. I'm obviously not very good with using this computer. There you go. So there's pi in sexagesimal. If you wanted pi times, let's say times 1,000, oops. Is that 1,000? Or, no, that wasn't 1,000. Something's wrong there. Let me just put in something here. Something is wrong because that is, well, anyway. Oh, I see what I did. No, I don't know why it's flaking out on pi. But if I just, oops. I don't know what's going on with that. Oh, because it's a chord. Of course, it's the wrong sort of thing. If I just, yeah, you can't have a chord function that's that high. So if I just do that as take a different function. I don't know, something like that. That gives you that number in one format of sexagesimal. You can do it in another format of sexagesimal. Oops, that's an error. That is an error. I forgot to put a comma in there. Sorry. Yes. So there it will represent it as sexagesimal number where the decimal part is, as in Ptolemy, is a whole number. So there are lots of different ways. And using this, you can take, let's say, let me just show you a system A table. You can take a system A table and let me get this set up so that it's acting. Well, I guess I'm showing you a system B table. Okay. So you can just take a table, let's say here, and expand it. And expand it as far as you like to any year you want. And you can expand it in both directions. And this enables you to, something's wrong here. What's going on? Let me just kill that and try it this way. Oh, that's what's wrong. There we go. I think I need to do it without having a mouse. Okay, here we go. So you can just sort of expand it any number of years you want. It's not very fast because this is an old Mac. But the problem is this. It'll take a while to do it. But the problem is this. Microsoft has actually blocked this. So you can no longer do this on a Mac. And there's no web-based spreadsheet where you can do this sort of thing. So has this, yeah, it's now showing you the System A thing to 362 and beyond. This would enable you to try to understand, to compare these models, these tables with other tables. Unfortunately, as I said, this is a place where the technology has actually gotten worse. So anyway, that's where we are. Let me conclude with some small observations. I think I'm out of time now.
Yeah, is there 10 minutes?
Oh, well, it's okay. So the first question is what place there is for these presentations, these digital modelings. And one possibility is a project proposal of Alan Bowen and Francesca Rockberg to put together an early knowledge of the heavens, a digital library for Mediterranean, Near Eastern, and South Asian contexts in pre-modern times. So that's the first thing that might happen. If they actually get that project funded, then this would be a part of the project. Second problem is to solve the spreadsheet problem, and I don't know how to do that, but presumably someone in the near future will start saying we need to have more flexible spreadsheets, and preferably spreadsheets that are based on something like the Google version of spreadsheets. And of course, in the very distant future, there will be genuine three-dimensional projections, the modern version of a physical model, which of course is much too expensive for someone to play with, but with modern technologies, you can have three-dimensional glasses and 3D glasses and do all these sorts of things. So anyway, that's it. Thank you.